Section: Introduction. In this section, we formally define the SOTOPIA environment, focusing on social interactions, their observation and action spaces, and social evaluations. This definition emphasizes the partial observability and multidimensional aspects of social interactions. For social interaction, we consider two participants, A and B, and model it as a partially observable Markov decision process, or POMDP. This is represented by a set of possible social states, an action space, and an observation space. The transition function describes how we move from one state to another based on actions, while the observation function indicates what can be perceived from a given state. The reward function reflects the quality of the interaction based on each agent's private goals, like successful persuasion or mutual understanding. In SOTOPIA, the observation space consists of the dialogue history. Each agent operates with partial observability, receiving private observations at each time step. These observations include all the dialogue histories and contextual cues that the agent can perceive, but they do not include hidden factors like the partner's private goals or emotions. The observations are generated by a probabilistic function that captures the asymmetric nature of social perception. A social episode for an agent includes the dialogue history and the actions taken during that time. An action in SOTOPIA is defined as any form of communication, whether verbal or non-verbal. Each agent has an action space that includes all possible communicative behaviors. At each turn, the agent selects an action based on its observations and private goals, and these actions contribute to the next observation. To optimize the social agent using methods based on Markov decision processes, we approximate the SOTOPIA environment. At each step, the state is represented by the dialogue history and the agent's social goal. The social policy generates a distribution over possible utterances, and offline rewards are used to train an online reward model. For social evaluation, the SOTOPIA environment provides quantitative feedback on how well each agent meets its goals through SOTOPIA-RL, which includes a multidimensional evaluation suite with a large language model evaluator. This evaluator produces a score based on the social episode and the agent's goal, indicating how well the agent achieves its social objectives. This score is expanded into a 7-dimensional vector that includes various aspects of social interaction quality, with the primary focus on goal completion. In the methodology section, we outline our proposed SOTOPIA-RL framework, which consists of two main components: designing social rewards using large language models and training social agents through reinforcement learning. The first component aims to provide high-quality offline reward labels for training, while the second focuses on optimizing the social agent's policy through reinforcement learning. Section Summary. In this section, we define the SOTOPIA environment as a partially observable Markov decision process that models social interactions, incorporating observation and action spaces along with a multidimensional evaluation system for assessing agents' performance. We also outline our SOTOPIA-RL framework, which focuses on social reward design and reinforcement learning to optimize agent policies based on dialogue history and private goals. Section: Social Reward Design with LLMs. In this section, we address the challenge of designing high-quality rewards for social interactions. We simplify this process in 2 steps. First, instead of scoring individual utterances based on the entire dialogue history, we link the overall outcome of the episode to each utterance, which helps reduce variability in our assessments. Second, we create a multi-dimensional rubric that clarifies how each utterance contributes to achieving goals. This breakdown transforms a complex task into smaller, more manageable evaluations that large language models, LLMs, can handle effectively, providing detailed and reliable feedback. For each social episode, our aim is to assign a reward to each utterance that reflects its role in the interaction. Episode-level rewards can be too broad since even poor quality utterances can lead to successful outcomes. Therefore, we perform a more precise attribution at the utterance level. Advanced LLMs evaluate each utterance within the context of the entire episode, giving us scores that range from 0 to 1. We then refine these scores based on the episode's outcome, highlighting strong utterances in successful episodes while still recognizing good contributions in less successful ones, albeit to a lesser extent. Next, we expand our reward system from a single score to multiple dimensions. While attributing a single reward improves detail, it doesn't fully capture the quality of an utterance. High-quality utterances not only help achieve goals but also enhance engagement and maintain the flow of conversation. To reflect these broader contributions, we include additional dimensions from our evaluation framework. Specifically, we assess relationship maintenance, which looks at whether the interaction strengthens the relationship between agents, and knowledge seeking, which evaluates whether the agents gain new insights during their conversation. These dimensions are important as they encourage collaborative interactions and indirectly support goal achievement. Overall, we start with a single episode-level reward and expand it to create more detailed, multidimensional rewards that reflect the quality of each contribution. This design is offline, meaning it uses the complete dialogue context after the episode ends, allowing for better evaluation without the unpredictability of real-time feedback. It is also flexible, as we can add more dimensions and adapt it to various social contexts, such as emphasizing relationship building in therapy or focusing on knowledge acquisition in education. In the next stages, we connect our social reward design to the training of social agents. We distill the knowledge from our offline rewards into a reward model that provides real-time feedback on utterances, enabling efficient training while allowing the policy to understand the underlying social context. Directly applying complex models to LLM training is not feasible due to the computational challenges, so we use a more manageable approach that still captures essential social factors. We train our reward model to provide feedback based on the dialogue history, allowing it to infer hidden social cues from local observations. This model helps us give accurate, detailed feedback for reinforcement learning optimization while still considering the social dimensions that a more complex model would address. Finally, we train our social agent policy using this reward model, focusing on providing feedback at the utterance level. We begin by warming up the policy through behavior cloning to ensure coherent responses, then continue training with a method that emphasizes efficiency. Each interaction is broken down into pairs of states and actions, and at each step, the policy generates responses, receives feedback, and updates to maximize expected rewards. We streamline the process to focus on optimizing utterances effectively, allowing the agent to perform better in multi-turn interactions despite the simplified training approach. Section Summary. In this section, we address the challenges of designing high-quality rewards for social interactions by simplifying the process into two steps. First, we assign episode-level outcomes to individual utterances to reduce variance, and second, we introduce a multidimensional rubric that evaluates utterances based on their contributions to goal achievement, relationship maintenance, and knowledge seeking. This approach allows us to create reliable, fine-grained supervision for training social agents using reinforcement learning while effectively capturing the complexities of social interactions. Section: Experimental Settings. In this section, we outline our experimental settings. For our model, we chose Qwen 2.5-7b Instruct as the base large language model, LLM, for training both the policy and reward models. We utilized GPT-4o as the judge in our SOTOPIA-RL evaluations. We evaluated our method using two configurations of the SOTOPIA benchmark, SOTOPIA Hard, which includes 14 challenging social scenarios, and SOTOPIA-AL, which covers 90 scenarios. For SOTOPIA Hard, we used 10 different agent pairings per scenario, while for SOTOPIA-AL, we employed 2 agent combinations per scenario to ensure diversity and scalability. More statistical details can be found in the appendix. To compare our training methods, we included several baselines: behavior cloning, BC, using social interaction data from GPT-4o, SOTOPIA-PI, which combines behavior cloning and self-reinforcement, and other recent methods like PPDPP, EPO, DAT, and DSI. Our approach, SOTOPIA-RL, integrates direct attribution of utterances with a multidimensional reward design, trained using single-turn online reinforcement learning without explicit reasoning. For reward attribution, we compared our strategy against 4 baselines that define how utterance-level rewards are derived from episode-level scores. These include uniform rewards, singular rewards for one selected utterance, scaled rewards distributed proportionally, and direct attribution with normalized weights. Our method, used in SOTOPIA-RL, is detailed in the appendix. In terms of reward combination, we trained our reward model using 3 dimensions: relationship maintenance, knowledge seeking, and goal completion. We found that averaging these 3 signals allowed us to validate the benefits of multidimensional reward modeling. A more detailed weighting would require extensive hyperparameter searches, which are computationally intensive. Our results show that SOTOPIA-RL establishes state-of-the-art social agents on the SOTOPIA benchmark. Specifically, QWEN 2.5 to 7b instruct trained with SOTOPIA-RL achieved the highest goal completion score of 7.17 in SOTOPIA hard, indicating that our utterance-level reward model enhances RL training. We also noted that improving single-turn interactions can effectively optimize multi-turn performance. While AMPO achieved a score of 7.50 on SOTOPIA hard, it relies on an explicit reasoning process and requires significantly more tokens per utterance, making it an unfair comparison to our method, which uses GRPO for utterance generation without additional reasoning tokens. Our training pipeline, which begins with GPT-based self-play and offline reward annotations, shows that SOTOPIA-RL not only matches but exceeds GPT-4o's performance when used directly as a policy model. If SOTOPIA-RL were merely a stronger form of distillation, it would not surpass GPT-4o. We found that our reward attribution methods significantly improved goal completion scores, demonstrating the importance of fine-grained rewards during RL training. Additionally, allowing LLMs more freedom in score assignment led to better performance. Finally, training with multiple reward dimensions greatly enhanced performance compared to using a single dimension. The best results came from combining all 3 dimensions, indicating that multi-objective reinforcement learning encourages a balanced approach to interaction quality. Optimizing each dimension independently also improved overall performance, suggesting that these objectives are interconnected, making our reward model training more robust. Section Summary. In this section, we detail our experimental settings, using QWEN 2.5-7b instruct as the base LLM for training our policy and reward models, and evaluate our method on the SOTOPIA benchmark with 2 configurations. Our proposed SOTOPIA-RL approach, which incorporates direct utterance-level attribution and a multidimensional reward combination, outperforms existing methods, demonstrating the effectiveness of our training strategies and reward attribution in enhancing social agent performance. Section: Discussion. In this section, we evaluate the effectiveness of SOTOPIA-RL by first confirming that its performance improvements are genuine and not due to reward hacking. We analyze how our enhancements stem from the design of reward attribution and reward combination. For our first research question, we find that SOTOPIA-RL develops high-quality social skills rather than simply fitting to specific partner or evaluator models. Reward hacking would mean that performance gains are limited to certain models and do not apply to human interactions. Our analysis shows that SOTOPIA-RL's performance improvements are consistent across various partner and evaluator models, indicating strong robustness. Additionally, these gains are validated through human evaluations, confirming they are not just artifacts of the evaluators. We also provide further evidence in our safety and diversity evaluations, showing that our trained model remains safe and diverse without shortcut degeneration. For our second research question, we discover that effective reward design relies on offline attribution rather than just using a strong language model. Social interactions cannot be fully assessed based solely on previous dialogue. The quality of an utterance depends on the entire conversation. Therefore, we assign episode-level rewards to each utterance using information from the whole dialogue, which is inherently offline. Our comparison of training methods shows that the offline approach significantly outperforms the online method, demonstrating its effectiveness. Notably, this improvement does not depend on using advanced models, as even weaker models can produce reliable reward signals with well-designed prompts. For our third research question, we explore why combining rewards leads to improvements. Using multiple reward dimensions enhances the robustness of our reward model and helps prevent overfitting in reinforcement learning. We rule out the possibility that our gains are simply due to smoother reward labels by testing different scales of reward attribution. Our findings indicate that finer scaling does not lead to better performance. We also find that models trained on different reward types capture distinct aspects of social interactions, and combining them allows for a richer understanding of social signals. Furthermore, training with combined rewards stabilizes the learning process and contributes to consistent improvements. In our qualitative analysis, we examine a multi-turn interaction where our model, Naomi, persuades another model, Sophia, to share a blanket during a cold night. This example illustrates how our social agent can generate utterances that address multiple social dimensions simultaneously. For instance, Naomi's statements not only pursue her goal but also strengthen their relationship and show her willingness to adapt. These utterances demonstrate how our trained agent effectively integrates goal pursuit with friendliness and informativeness. Additional case studies are available in the appendix.